Hello everyone. In this video we will be reviewing week 1 of the content from Math 277, which is talking about vector functions in 2 and 3 spaces. We're going to also talk a bit about space curves as well, and a little bit about how they can be interpreted and how you can use given functions to solve for motion such as position, velocity, acceleration, speed, and arc length. So first things first, we're going to do a little bit of a recap from other previous calculus topics. A lot of this should be familiar to you. So we're going to talk about some derivative rules that we have for vector functions. It's going to be pretty straightforward. It's pretty much things you are already used to. So the first thing we will be covering is our sum and difference rule. So this is the same thing that you are already used to. So if you had, let's say, u squared, actually no, let's do x. I don't know why I chose u. Sorry. If you had x squared plus 2x to the power of 9 plus 1/2 x to the negative 2, then that's basically just taking the derivative of each term on its own. But we already knew that, so that would be coefficient comes down, exponent reduces by 1, right, multiplied by the coefficient, so that would be 18 to the 8 plus, so then this is negative 2 over 2, so then that's saying minus 1x to the negative 1. Right, so that is our sum and difference rule. Next we have our, we have our scalar multiplication. So our product rule is also another word that we use for this. So this is saying if we had u and v multiplied, it's a different color, u multiplied by v, and we wanted to take the derivative of that, right? So if we wanted to take the derivative of this right here, we would have the first term times the derivative of the second term, and that's plus the second term on its own times the first term's derivative. All right, so that is our scalar multiplication rule. So if we were to use, let's say, as an example, we used 2x squared times 3x. So that means we would have to, actually no, wait, sorry, that's a bad example. You know what? I will not do an example for this. I think you guys know. So sorry to those of you watching. This is a very turbulent video. Okay, so we will not be dealing with quotient rule for this kind of math, thankfully. So that's going to give you guys a bit of a break. But in its place, we have some different kinds of multiplication rules. So next we are going to be taking a look at dot product rule. So this is similar to our other example. So if we had u, now with a dot, v, then this would mean that we would have to use dot product in its place. So we're going to have two terms again. Right, in the first term, we have u prime, the dot product of v. And then in the second term, we have the derivative of v with the dot product of u. In the same vein, we also have cross product. So we take the cross product derivative. Sorry, I should probably indicate this as a derivative. So when we do that for our cross product, same kind of thing, I'm sure you can infer. So we take the derivative. This time we would be using, so this is u cross v. That means we are going to have the derivative of u with the cross product of v, and we're going to have the derivative of v cross product with u. So basically, with these three multiplication rules, whether it's scalar, dot product, or cross product multiplication, they pretty much follow the same rule, just you're using a different operation to achieve that multiplication between each of those terms. All right, and lastly, we have chain rule, which I'm sure you should all be familiar with. It's a little different though. So if we had chain rule, so I want you just to consider something that looks like this. So if we had u in a different color, we had our function. So we're going to treat it as like two different kinds of things. So we're going to take the derivative of this. We would take the outside, I'm going to put that first. Then we're going to have our inside. And then that's times our derivative of the inside function. Right, so it is a little different than what we're used to, but again, simple stuff, not too hard. Okay, so now we're going to talk about motion in 2 and 3 space, now that we have a little bit of a warm-up. So what we can do to think about functions and how they relate to, I guess, different curves when we're going to be asked about that, is to imagine in a 3-dimensional space, to think about a curve C. We call this a space curve. So this is a space curve. We can imagine having different functions for position based on time. So let's say this is t, so position at maybe t equals 0. Maybe this is our position at t1 and our position at t3, right? No, t2, sorry. So that's the significance of our curves and how they relate to our position functions. So that's how you're going to be able to, I guess, digest this material. So I'm going to write that down really quickly. So space curve is the path the position vectors, position vectors, I guess vector functions, trace with time. So this is called a space curve. And yeah, so just some notation things. Taking another look at our space curve. If you have a space curve that starts at P and ends at Q, usually there'll be a couple arrows to indicate the direction. So say if on an axis we drew their points, say this is at A and this is at B, right? So we would say this curve exists on closed interval A and B. So if we were to write this out, we could equivalent this to saying P is equal to the position at A and Q is equal to position at B. If you are given a curve where the starting points and end points are the same, then that means it's a closed loop. Right? Soon this will all make a little more sense. So now we're going to move on to some practice questions. Oh, sorry, there's another thing I needed to cover before we do that, obviously. So when we were talking about motion in 2 and 3 space, we want to consider some equations for it. So I'm just going to erase some of these notes here, just so we have a little more room to write. I'm sure you guys understand all of this stuff here. We're going to get rid of that to make way for some equations. So, motion equations. So some of this should look familiar to you from previous calculus classes, but in case you forgot, no worries. I'll walk you through each one. So our most bare bones one is position. Can't really break it down any further. So position we denote with an R, an arrow over it, T. So this is position. And when we write it, you're going to see many different forms. Usually we use the IJK direction vectors to show, I guess, its orientation in space. But yeah, that is the most basic form of motion. Then next we have, so if we were to derive it, we would get velocity. So velocity we denote with a V arrow above it. And this is equivalent to taking the derivative of r, or our position. Or you can think of it as like this. So if you had it in IJK form, you would just derive each individual term as needed. Then if we were to derive velocity, we would get acceleration. So acceleration, we use A, that's equal to dv over dt for our velocity. Right? It's also equal to taking v prime. So if you start from position and you derive, then you'll get velocity. Then deriving from velocity, you'll get acceleration. If we went the other way, you would have to integrate. Okay, a couple other equations. We have speed, which is just going to be vt, which is our velocity as magnitude. Then lastly, we have arc length, which requires you to find speed, so denote that as L, and that's equal to the integral of our speed dt. Right, so we use our knowledge of space curves and vector functions in order to derive values and equations for motions of particles. So let's try an easy example to start us off. So we have a position vector. Here we go. Got a position vector of a particle given by this equation here. And we want to find velocity, acceleration, and speed at point 0, 2, 4. So first things first, we aren't really given a value for t. So we are given a point, but we don't actually have an explicit value for t. So that means our first step is to find t. So I'm going to write this out. So our position vector, so we're just starting with position first. T squared minus 2t, I direction, plus 6t minus 10, j direction, plus, I'm going to rewrite this. This is, actually no, I'm not going to rewrite this. That was a lie. That was a lie. In the k direction. So we're going to deal with, so we're going to work with each term on its own. So first we're going to start with this term here. And we know that our point is equal to 0, 2, 4. So what we are going to do with this knowledge, we are going to use each of the x terms for each one. So this is x, y, z. And just keep it together with the x term from our position vector. So if we did this term right here, we want it to equal 0. So we want it to equal each respective component of that point. So we do 0 equals t squared, this is from our position vector, minus 2t. Let's do the same with the second one, right here. So that would be, so we want it to equal 2 now, because that's our y component of our point. So that's 2 equals 6t minus 10. And lastly, our k term. And that means we will want 4 to equal square root 2 t 3 over 2. So we want to find a common value for t that is shared by all of these. So find common t. That makes this equation true. So let's do our first one. So we move that to 2t to the other side, t squared. That gives us, actually, hold on. That was a bad way to go about this. I apologize. So we can factor out t, got t minus 2, right? So that gives us 2 of them. That gives us 2 t's. We have t equals 0 and t equals 2. So we're just going to hold on to those, because depending on what we get for the other equations, that will probably change. So if we move that over, we got 12, 6t, and here t only has one solution as 2. Right, so if we're starting to see a pattern here, and I'm not going to bother with the other one, but if you really want to, try plugging in 2 for t and see where that gets you. So let's try that. Square root 2 times then 2 to the power of 3 over 2, and that gives us 4, right? So you can just test it out. Test t equals 2. And how do we know to use t equals 2? Well, for both of our equations, t equals 2 is a common value, right? So now we know t is equal to 2. Next step, now we can actually start looking for velocity, acceleration, and speed. So let's find velocity, knowing what we know. So we are going to derive each term, so each of our I, j, and k terms, using our rules. So velocity is equal to first term, t2 minus t. Next term, 6. And it's just plain 6 because the rest turns to 0. And then plus, so we're going to have 2 root 2. That 3 over 2 comes down. And then this is going to reduce to t half k. All right, so that is our first step. And now we can plug in our values, plug point, to find what we are looking for. So that would be, oh yeah, so plug, sorry, that's wrong, not our point. We're going to plug t that we solved. So that would be, so that's 4 minus 2. So that's 4 minus 2, 4 minus 2, I plus 6, j plus 2 times 3 over 2 times 2 to the power, sorry, to the half. Okay. So that will give us, I'm not sure why I need to change color. So that's 2i plus 6j. And so this is going to turn into 2, right? To the power, so this is like square root of 2 times square root of 2 over here. So that just turns into 2 over 2, that cancels. So that just turns into 3k. And we can write that out as coordinates, which is 2, 6, 3 for velocity. So next step, let's find velocity. Nope, not velocity. We just did that one. Acceleration. So now we're going to derive each of these functions that we found. So that is 2i plus 0j plus, I'm going to write this out a bit better. So that's 3 over 2 square root of 2 times square root t, or t to the power negative. Sorry, t to the power half. So this comes down. So that's 3 over 4 when that comes down times square root 2. This reduces. To the negative 1 over 2. All right. So now when we plug in for t, that's going to give 2, 0. And then what happens here? 3 over 4, square root 2 over square root 2. Those go away. And this is 3 over 4 for our k. Right? And lastly, we are asked to find the speed of the particle. So that's nice and easy. So we are just taking the magnitude of that. So it's going to equal, wrong notation, that is equal to the square root of 2 squared plus 6 squared plus 3 squared, which is equal to 4 plus 9 plus 36, which is equal to square root of 49, which we know to be 7. Right, so those are our answers here for acceleration and for speed. So that was a nice and easy example. So now we're asked to find the Cartesian equation for the line tangent, the line tangent to the plane curve given parametrically as such at this point. So this question has a couple more steps in it than we are usually used to. So first thing I want you to be aware of is this equation right here. So this is one we need to convert to our Cartesian equation, right? We're going to be needing this. So you're going to have r naught, so that's our initial position, plus some variable times velocity. So that means there's a couple things we have to find. So we have to find what our RO is, our R naught. So let's do that first. Let's find R naught first. So basically, we are just going to put our value for t right into there. So 3 square root 2 sine pi over 4 I plus 1 plus 2 cos, then that's 2 times pi over 4 j. All right, let's simplify a couple things out. So we know that this is 1 over square root 2. And then that's plus 1 plus 2. And this is, when we simplify this a little bit more, this is pi over 2, which is 90 degrees. We know 90 degrees cos is 1. So that's just 1 plus 2. And then that gives us, so these cancel out. So that's 3 and 3. If I am not mistaken, I will check. Sorry, I've made a mistake. I was thinking sine. Sorry. So at 90 degrees, cos is equal to 0, right? Because we are not traveling in x direction. Sorry. So this is 1 plus 2 times 0. So that would make this 1. Sorry about that. Now let's find our velocity next. So that should be easy enough. Let's derive this equation up here. So that's 3 square root 2 changes the cos t, and that's plus 1 goes away, right, because it's a constant. So then that's negative 2 sine 2t times 2. This I, this is our j. So that means when we plug in for our t value, we've got 1 over square root 2 again, plus negative 2 sine pi over 2 times 2 j. So again, square root 2's cancel. So we're going to have 3. That's our x-coordinate. And sine is 1 at 90. So then this is just going to be -4. So now we are going to make our equation. And once we do that, we be needing to use our values that we found. So first things first, we are going to be using our R naught. So this is 3 and 1. Then we need to use what we found for our velocity, right? And now we're going to separate our x and our y values. So what do we mean with that? So we are going to be taking just these parts and making it equal to our RT. So you can think of RT as having both an x part and a y part. It's going to make it equal to each component. So let's just work with our x green components. So that's x equals 3 plus 3t. And y, that is y equals 1 minus 4t. So now that we have our components, let's isolate for t. So then we can solve for each one. Isolate t, equate equations, and then you'll get your Cartesian equation. So let's just work with x first. Let's move everything over. So we have x minus 3 over 3 equals t. And then for y, we have y minus 1 divided by -4 equals t. Right? And we want to make these equal to each other. So let's do x minus 3 over 3 equals -y plus 1 over 4. And now we can just rearrange to create what we need. So we're going to cross multiply and divide. And that's going to give 4x minus 12 equals -3y plus 3. Move things around a bit more. 3y minus 4x. So I move everything to this side. So it's plus 4x. Move this to that side. Minus 15 equals 0. That is our final answer. All right, so that is our second example done. Moving on. This one's nice and easy as well. Yeah, so let's try our hand at this one. So let's try A. Right, so given this equation, let's find velocity and acceleration and speed. I think we're actually apt enough to skip over that one. What I'd like to do is determine distance traveled from point P, 1, 0, 0 to Q, -5, 9, 9. So, how do we go about doing this? Right, so this is similar to what we just worked with when we have our point plus velocity times t, or times some parametric variable. So what we're going to be doing for this one, let me just get rid of this for a second. We're going to make each of these points equal to our space curve. Right, so make each point equal to the position equation. We're going to be solving for t. So let's start with p first, in red. So we are going to want to make this equal to 1 minus 2t I plus 1 over 3 t3j plus t squared k. And what this is going to do, this is going to help us find integration boundaries. So this will find our integration bounds because we are looking for distance traveled, which is arc length, right? Which requires you to have different bounds for that integral. All right, so this is the same kind of thing that we did up here, right? Where we had to kind of isolate each separate component. So we're going to do the same thing for that. So using our x components here, we know that 1 is equal to 1 minus 2t, solve for t. So that's t equals 0. Next one, y component, 0 equals 1 over 3t to the 3, t equals 0. And lastly, 0 equals t squared, t equals 0. Right, so that is our bottom bound, right, because we can't go below 0. So now we are going to work with q. Hopefully I have enough room for this. So now we're going to make everything equivalent to our point q. Sorry, it's so messy. That should be an I plus 1 over 3t cubed j plus t squared k. So negative 5 equals 1 minus 2t. And then that gives us, so negative 6. So t is equal to 3. Then we have 9 equals 1 over 3t cubed. So that gives us 27 equals t cubed. T equals 3. And then lastly, t squared. And then t is equal to 3. So this is the top part of our integration bound. So now, all I have to do is solve for arc length. Sorry, just checking out what the other ones are. So solving for arc length, L equals speed dt. Right, so I'm just going to plug in what speed is so we can save a little bit. But just know that what we solved for, so t equals 0 and t equals 3, are going to be our top and bottom bounds. So give me a second. You should be able to find find speed on your own. I'm just going to plug it in for time's sake. All right, so we have t squared plus 2. So it's t squared plus 2. And when we integrate that, that's going to give us, okay, that's t to 3 over 3 plus 2t, and that's from 3, 0. So that's like saying 3 cubed over 3 plus 2, 3 and that's going to be 0 for the other term. So what is that? That's 27 divided by 3, which should be 9, plus 2 times 3, 6. So that should equal 15 units. All right, so that is how to use 2 points to find something like that. Let's see, I want to revisit question 3 again. So for this question, the first thing that we will be needing to do is to find our value of t. Find t. So basically we are going to be doing that by just taking our x components of our given point and equating it to our parametric x equation. So I want -1 to equal 2t squared plus 12t plus 17. Right, so when we move that over, that gives -18 equals 2t squared plus 12t. Let's move that back over. It's plus 12t plus 18. Let's factor out that 2. 2, and that gives plus 6 plus 9, 6t. And that's equal to 2 times t plus 3 squared. T plus 3 squared. And we know that t must then be equal to -3. Let's do the same with y. Equate it to 0. So that gives us 0 equals t cubed plus 6 plus 9t. All right, let's factor out that t. So this one's going to have 2 solutions, or even maybe 3. Plus 6t plus 9. Same thing. T is equal to, so this is the same thing over here, right? So t is equal to -3, or t is equal to 0. But since -3 is common for both of them, we are going to use t equals -3 for our value of t. So now what we can do, here's a little bit of a shortcut. So we're going to find slope, right? For our equation, we rewrite this as a Cartesian form. So a lot of you have seen maybe this equation here, also written as y2 minus y1 over x2 minus x1. But we can equate this to being the derivative of y over the derivative of x, and we can use that to help us find what that is meant to be, and we will be using t to plug in to find out what that is. So with our y on top, that means we'd have to derive this equation right here. So what does that look like? That's 3t squared plus 12t plus 9 over, that's 4t plus 12, and then the 17 goes away. So this is basically from our y, and this is from our x. So let's plug -3 and see what happens. So that's 9, nope, that's 27. 27 minus 36 plus 9. 27 minus 36 plus 9, and that equals 0 on top. On the bottom, we have -12 plus 12 also equals 0. So what do we do when we have something that's 0 over 0? Well, not to fret, because we can use L'Hopital's rule. So I'm just going to put that as a third step. We can use L'Hopital's rule. So that means we're just going to have to derive another step. So let's do plus 12, and eventually we're going to get where we want. Let's try now. So this is negative 18 plus 12. Okay, we're getting somewhere, over 4. This is negative 3 over 2, right? So we're good there. We can stop there. And this is our slope. Slope. All right. And now we are going to use point slope form to just write our equation. So point slope is given by y minus y1 equals mx minus x1. So we write that out. That's y minus, and we're going to use our given y from the top, 0. Our slope that we just found, x minus negative 1. It's like saying plus 1. And you can just write this out. So our final equals y negative 3 over 2 x minus 3 over 2. Okay, so that is our final answer for this question. So we've had some experience working with starting with a position vector and going to find velocity and acceleration. But now what happens when we want to go backwards? What if we're given acceleration and we want to go backwards to find velocity and go further back to find position? All right, so let's talk a little bit about that. So working backwards, so we're going to use this example right here. Take a second to look at that and think about how you would do it. So to start this question off, the first thing that we will need to do is to integrate our acceleration to get velocity, right? Because we are working backwards. So we want to find the indefinite integral. And I'm pretty sure, since we're not given any value for t, then we want to keep this in terms of t. So we're not actually going to get a real number answer. I think it's going to stay in terms of t. So what is that going to look like? I will show you. So integral of acceleration to get velocity. Right? So we are going to take, it's 4t, 6t, and then that's just 1. Right? What does that look like? That is 2t squared. That is, 3t squared, and then we have t, right? But since this is an indefinite integral, we also have this c here. Okay, and so now that we have that, we still have this constant c at the end. So what do we do with that? So next step is find c. So using this equation here, we can equate them together, right? So this is v at 0. So the first thing we want to do is find what this is at 0. And we know that if we move that to the other side, that would be c. So c, actually no, sorry, that's a lie. So we want this to equal that plus c. So equal all of this, right? So we just take the coefficient, that's 1, negative 1, 1 from here. Now if we take this whole lot right here, and we know that t is equal to 0. So let's plug that in for here, and that gives us 0, 0, 0, plus our c. And now just do some simple math. So that's 1 minus 0, 1. That's negative 1 minus 0, and 1 minus 0. is c. Right, so now we know that is our c. So now we want to put it back into equation. So we know that v, once we integrated it with respect to t, we have 2t squared 3t squared t plus that value of c that we just found, 1, negative 1, 1. So now we are going to take each component and we're going to combine them together. So that gives 2t squared plus 1. And then that's I. Then we have 3t squared minus 1. That's j. And we have t plus 1 k. All right, and that is our final answer for our velocity. Right, so I'm going to do another example up here. To work backwards, we're going to try our hand at this one, knowing what we know now. And let's just start with velocity first, all right? So we're going to focus just on velocity, then we're going to go back for our position to solve, right? And then that will wrap up this review. There's a couple other practice questions to try out, but to keep it short, I will not be doing them. I'm going to stick to, actually, I might be doing 11. Right, so we're going to do a couple more examples, working backwards, and then I'm going to do 11. Okay, working backwards. So, if we remember what to do, first thing that we'll need to do is we're going to do indefinite integral of our acceleration to find our v. So, t is equal to integral of 6t for the negative 2 over t cubed dt. So that turns into 3t squared, 4t, and then what to make of this? This is like, say, negative 2t to the negative 3. So when we integrate that, it's t to the negative 2, negative 2 over negative 2. So that's just t to the negative 2, negative 2. All right, and of course, we can't forget our plus c. So this is always the catch. Now we need to find c. So we are given what velocity is at 1. So that means we want to make this over here. So that's 1, 2, negative 3, just looking at the coefficients for each of those. We're going to make that equal to whatever we got up here. And knowing that t is 1, let's plug that in. So then that gives us 3, 4, 1 plus c. And we are going to find what c is. So let's do 1 minus 3, negative 2, 2 minus 4, negative 2, and negative 3 minus 1, negative 4. Putting this back into our equation, we're going to find what velocity is. So then that's v equals, so that's 3t squared, 4t, t to the negative 2, plus what we just found as our c, which is negative 2, negative 2, negative 4. Throw it all together, that gives us v equals So it's 3t squared minus 2I plus 4t minus 2j plus t to the negative 2 minus 4k. All right, and that was just for velocity, but I think we can challenge ourselves and try position next. So let's do that. So it's the same kind of steps. So I'm just going to draw a little separation here. So let's start with our indefinite integral. So we're going to be using what we just solved, and we are going to be integrating that. So that means we have to go minus 2, and that's 4t minus 2, and that's t minus 2 minus 4. Right, when we integrate that, that will give us t 3 minus 2t. That will be 2t squared minus 2t. And then this will be negative t to the negative 1 minus 4t plus c, or plus d, because we already used plus c, but honestly it doesn't really matter as long as you can keep it straight in your head. Right? Then for 2, we are given this up here, so it's basically the same kind of thing that we did before. So we want this to equal 1, 2, and then we're just going to throw in a 0 because we're not given a k. Right? This is going to equal t 2t squared minus 2t. So this step is a little bigger than our last question, but you can do it. I believe in you. So then what we're going to be doing next, plug in 1 for t. So this is, that's 1 minus 2, negative 1. And then that's 2 minus 2, got 0. Got 1 minus 4. Yeah, 1 minus 4, negative 3, plus d. So that means d is equal to 1 plus 1, 2. 2 minus 0, 2. Then we move that to the other side. That is 3. And now we can throw it all together. So then this is equal to, and I'm just going to do this step all together, plus 2i plus 2t squared minus 2t plus 2j, then negative t to the negative 1 minus 4t plus 3k. Just going to check my answer. All right, and that is how to use that same process to find position from our velocity, which came from acceleration. All right, so we're going to do one last question. All right, so let's take a look at this one. So we want to find maximum and minimum speed for the particle. All right, so we're just going to do part A for interest of time. So the very first thing that we can do, we can just find what our equation for velocity is. Nice and easy. Let's get that started. So that's going to be 4, negative 3 sine t, and 2 cos t. All right. So now that we have velocity, we can find speed. So when we do speed, we can have 4 squared plus negative 3 sine t squared plus 2 cos t squared. Now we have both sine and cos, but let's just reduce it down just to one of them. So we're going to use our trig ID, sine squared plus cos squared equals 1. And we're going to substitute that in. So let's substitute, I think I like sine better. So let's substitute cos. 1 minus sine squared. So let's simplify this down and then we can plug it in. So that's 16 plus 9 sine squared t plus 4 cos squared t. Right, and we're going to substitute that trig identity in. So we have 16 plus 9 sine squared. This one can stay plus. So we're still going to have 4. We're substituting 1 minus sine squared in place of cos squared. And what does that give us? That will give us 16 plus 9 sine squared t plus 4 minus 4 sine squared t. This gives us, this is a bit of a process, you know, so that's 20 plus 5 sine squared t, still going, we can do it. Actually, no, we can end it right here. So then our next step is to think about our largest value of sine and our smallest value of sine, right? To either maximize or minimize this. So when you think about our Cartesian, so let's only worry about positive stuff, only worry about stuff that's happening up here, right? Sine is at a minimum at pi and at 0, and at a maximum at pi over 2 at 90 degrees. Right? Where sine of that will equal 1, and then sine of this will equal 0. So if we plug those in for t, we will either have 1 or 0. So basically that's just what they want us to think about. So if we plugged in for 1, right, so if we have sine squared pi over 2, when it's at its maximum, so we want to maximize it, right, because that is the peak of our circle. Okay, I should write maximum. So that's going to be equal to 20 plus 5 times 1, which is equal to square root 25, otherwise known as 5. Then we do minimum. So minimum, let's just use 0 for simplicity, plus 5 sine squared. Sine of 0, we know that to be 0, so that's just going to be square root 20. And that is our minimum speed and our maximum speed. All right, so that is the end of this video. There are some more example questions to look through. I'm going to save those for later, but this should give you everything that you need to get started on the worksheets and the review. Thanks for watching.